Okay, a lot of people had questions on or trouble with the last two homework problems in section 10.6 on parametric equations, the applications. So I just wanted to quickly go over those and at least show you guys how to set them up, and then maybe I'll leave the math to you guys. So let's see. The first one we had, number 50 in your book, and I know I'm a little off screen here, but I'm going to be referring to your book to get the problem. A hospital is located 3 miles west and 4 miles north of the center of town. Okay? So, your book says, let the center of town be the center right there. And the hospital is located 3 miles west and I think it's 4 miles north. Yep. So then, just with our axis, that's the point, -3, 4, and that's the hospital. Okay? Suppose that a medevac helicopter flies at a constant speed from the hospital to the location of an accident 15 miles east and 20 miles south. 15 miles east and 20 miles south, we'll say is down here. 15, -20. And I'm going to fly from one location to the other. So, just to get an idea, it'll look something like that. And obviously, I'm going to fly this way. So, and it does that in 15 minutes. Choose a coordinate system with the origin at the center of town. We have that. Write parametric equations to represent the path of the helicopter as a function of the time after the helicopter leaves the hospital. So let's see. And we'll just put, just so we know for later on, the trip takes 15 minutes. So that's all the data in the problem. Now we want to set it up. And as far as it goes, I guess we also know it's constant velocity, which actually is important. We need to come up with parametric equations, which means an equation for x in terms of time and y in terms of time. And if you think about it, what does x do? In terms of time, what does x do? X starts at -3 and it goes to 15, the x values. And they move at a constant rate because we have a constant velocity. Again, don't worry about this graph. This is a graph of xy. But in terms of time, x goes from -3 to 15, and it does it at a constant rate. All of you know if you have a constant rate, well, that means you have a linear equation, which means we should be able to come up with a linear equation, y equals mt plus b, to model the behavior of x. And I will state right here, because several of my in-class students also had trouble with this one, I'm aware the book does it differently. You can try to use the book if you want. Although being honest, given that most of you had trouble with it for your homework, I'm guessing the book didn't help. So this is just another way you can do it that I think actually is more straightforward and uses what you already know. So we know that should be the equation of a line. How do you find the equation of a line? You need the slope. I need 2 points. Well, again, we're not using those 2 points because those points are xy. We need points xt, or in this case, t is my x and x is my y. Again, keep all the letters straight in your head. That's the equation of a line. That's x, that's y, using the notation we're used to. But then we know when time is 0, when we start, the x value is -3. When time is, let's see, it says 15 minutes, but I think the hint in the book is let time be an hour. So in 1/4 of an hour, 15 minutes, x is 15. Now we have 2 points. Find the slope. Let's see, change in y. So 15 minus -3 over change in x, 1/4 minus 0. 15 minus -3 is 18, and that's 1/4. Then you multiply the 4 up top, then you get 72. Which means apparently my slope should be 72. Does that make sense? Well, if you think about it, the x starts at -3 and goes to +15. Over time, x is getting bigger, from a negative x value to a positive x value. Again, we're not looking at this graph, we're just looking at our x values. X gets bigger, which means the slope of the line should be positive. And that's what we got. So that's a good thing. Now for my equation, I just need an intercept. But I already have it right here. When time is 0, x is negative 3. So 72t minus 3. There's my equation. Using the exact same logic, you can find an equation for y. Y is certainly moving linearly. Again, it's going from here to here, from positive 4 to negative 20, and it's doing it at a constant velocity. So now I need points in terms of t and y. When time is 0, y is 4. When time is 1/4, 15 minutes later, y is negative 20. Find the slope. Minus 20 minus 4 over 1/4 minus 0. That's negative 24 over 1/4, which is negative 96. Which means my slope should be negative 96t. We'll worry about the intercept in a second. But before we do that, does that make sense? Should my slope be negative? Well, yeah, because the y values go from 4 to negative 20. So over time, they're getting smaller. If they're getting smaller, then my slope should be negative, and it is. So that's a good thing. As far as my intercept, again, we actually were given it right here. When time is 0, y is 4. Now you have a set of parametric equations that model this behavior, what x is and what y is at a given time. Now, I'm going to leave the second half of the problem to you guys. I think your book says, where is a helicopter located 10 minutes after leaving the hospital? Just plug in 10 minutes, but keep in mind, our time is in hours. We used 1/4 over here for 15 minutes. So 10 minutes in terms of hours is 1/6. So when time is 1/6, plug it in there, and you'll figure out where the helicopter is in terms of x and y. Good. The other problem. Let's see. So, a golfer tees off on level ground and hits the ball with an initial speed of 52 meters per second and an angle of 34 degrees above the horizontal. Choose a coordinate system with the origin at the point where the ball is struck. So, really quickly, I'm not going to solve these problems out. I'm just going to set them up. And then you guys can do the math to solve them once we have the equation set up. Because I want you to work through the math because you have to. So, here's my golf ball. I know it's red, but whatever. And I'm going to launch it, let's see, at an angle of 34 degrees. So, right about here. Above the horizontal. So, there's the horizontal. That's 34 degrees. And it has an initial velocity of 52 meters per second. And when we draw our coordinate axis, we're actually going to let that be the origin. So we'll just draw lines straight through there. I think that's all the information we're given. Let's see. T's off from level ground. We have that. Initial velocity of 52 meters per second, an angle of 34 degrees to the horizontal. We have that. Good, right? Parametric equations. Well, they are in your book, but the parametric equations for projectile motion, x equals b sub 0 cosine theta t plus x sub 0. And then y equals negative 1/2 gt squared plus v sub 0 sine theta t plus y sub 0. Keep in mind, that's a t, that's a plus. I know they can be hard to read because they look pretty much the same. But now, just fill in the data based on what we have. For x equals v sub 0, that's my initial velocity, which is 52. Cosine theta, that's cosine of 34 degrees. T plus x sub 0. What's x sub 0? Well, since I let my origin be the point where it was struck, the x is 0. It's at the origin. So there's actually no x sub 0. And there we go. There's my equation for x. For y equals negative 1/2 g. What's g? Keep in mind, we said the other day that as far as it goes, Your G changes based off of whether you're using the customary system in terms of feet per second or the metric system. This is in the metric system, so G has to be given in meters per second squared, and that is 9.8 meters per second squared. That's the acceleration due to gravity in meters per second squared. So we have negative 1/2 G t squared plus v sub 0. V sub 0 is 52. Sine theta, theta is still 34 degrees, times t, plus y sub 0. But again, we made the origin the point where the ball was struck, so the initial height is 0, so that disappears too. So now, these are my parametric equations. Admittedly, don't lose the t right there. Admittedly, that's not a nice number, but you can throw it into your calculator and get it. That's not a nice number. Neither is that, but you can throw it into your calculator and get it. Now to answer the questions, and again, I'm not going to do all the math out, but for part C, how long will the ball be in the air before it hits the ground? Well, when it hits the ground, its height is 0. Its height is y, so make y 0 and figure out what the time is. You can use a quadratic formula, but I would point out there's no constant term here, so there's a common t. You can factor that t out, and then you'll have a messy equation, but it's still linear, and you can solve it without the quadratic formula. Solve it, get your time, and you're good to go. The next one, approximate the horizontal distance that the ball travels before it hits the ground. Well, the horizontal distance is x. To find how far it travels at a given time t, I need a given time t. But here, the first part that I do will tell me when it hits the ground, so we know how far it travels until it hits the ground. Take the time I find here, plug it in there, and that will tell me my horizontal distance. When is the ball at its maximum height, and what is the maximum height? Then the maximum height is, well, the y value, because y is height. Which means I just want to know the maximum height of this equation, but that's a quadratic. Find the vertex, negative b over 2a. Again, it'll be messy, but who cares? Throw it into your calculator. To find when it's at its maximum height, do negative b over 2a. And then to find the maximum height, just take the value you get and stick it in there. Just like you did in 171 with regular quadratics. Okay, that should give you more than enough information to be able to solve the problems in your homework, and hopefully to understand them a little bit better. You will see problems like them again on the exam, and they are important, so I wanted to make sure to go over this so you guys could do it. And I would stress, as I pointed out to several of you on your homework, and I emailed a few of you, if you have any questions, feel free to stop by my office and ask questions in person if that works better.